Evidence that our universe is inside a black hole? Could scientists have just cracked the code proving our entire universe spins inside a gigantic black hole? Here's the bombshell. In 2025, physicists finally proved that angular momentum, the property that makes things spin, survives even at the quantum level when particles split apart. And this discovery provides the missing mechanism for how our universe could inherit the rotation of a parent black hole. Be sure to keep watching until the end of this video because I'm going to reveal how twisted neutron experiments could definitively prove whether we're spinning inside a cosmic black hole that creates universes. So don't click away. You won't want to miss these cutting-edge laboratory tests that could rewrite everything we know about reality. This breakthrough is absolutely massive for black hole cosmology. For context, the existing theory suggests our universe exists inside a rotating black hole, supported by JWST galaxy rotation patterns, holographic principal evidence, Einstein-Cartan torsion models, and quantum entanglement connections. But until now, scientists lack the experimental proof that quantum properties like angular momentum could actually transfer across cosmic boundaries. The 2025 experiment studied what happens when high-energy photons split into entangled particle pairs. Researchers discovered something remarkable. Even when a single photon breaks apart into two separate particles, the original angular momentum doesn't disappear. It gets perfectly preserved and shared between the new particles. This might sound like abstract physics, but it has profound implications for understanding how universes could form inside black holes. Think about what this means. When matter falls into a black hole, quantum mechanics tells us the information about that matter, including its spin properties, must be preserved somehow. The 2025 experiments prove this preservation happens even during the most extreme quantum processes. If a single photon can pass its angular momentum to its quantum offspring, imagine what happens when an entire collapsing star transfers its rotation to the universe that might form inside its resulting black hole. This discovery fills a critical gap that has been puzzling cosmologists for years. Previous models of black hole universes could explain many observed phenomena, cosmic microwave background patterns, galaxy alignments, even why our universe appears perfectly flat. But they struggled to maintain how a parent black hole's rotation could influence the structure of a child universe. The quantum angular momentum experiments provide that missing theoretical link. What makes this even more compelling is how the preserved spin manifests across vast distances through quantum entanglement. When particles become entangled, they share properties instantaneously, regardless of separation. The 2025 research reveals this entanglement specifically preserves angular momentum information, suggesting our universe's large-scale structure could maintain a quantum connection to the rotating black hole that birthed it. Consider the scale of this. Every spiral galaxy, every rotating star system, every spinning planet might be echoing the primordial rotation of our parent black hole. The angular momentum that makes Earth rotate, that creates hurricanes, that drive the spiral arms of the Milky Way, all of it could be inherited from a cosmic parent we could never directly observe. This isn't just theoretical speculation anymore. We have laboratory evidence that the quantum processes involved in black hole physics can preserve and transmit the exact properties needed to explain our universe's observed characteristics. Now that we've established how angular momentum survives quantum splitting, let's explore the massive implications this has for cosmic scale rotation. If a simple photon can pass its spin to a quantum offspring, imagine what happens when an entire rotating black hole gives birth to a universe. This is where Kerr black holes become absolutely crucial to understanding our cosmic origins. Kerr black holes aren't your typical stellar mass black holes. These are rotating giants that drag space-time itself around with their spin, creating what physicists call the ergosphere, a region where nothing can remain stationary relative to distant observers. When matter falls into a Kerr black hole, it doesn't simply disappear. The black hole's angular momentum gets transferred to the infalling material through gravitational coupling, creating a cosmic dance of spinning matter and twisted space-time. Here's where the 2025 quantum discoveries become game-changing. The mathematical models for Kerr black hole interiors show that angular momentum must be conserved throughout the collapse and potential rebound process. If our universe formed from such a rebound inside a rotating black hole, every bit of that primordial spin should have been inherited by our cosmic expansion. This isn't just theoretical speculation anymore. We have quantum experimental proof that angular momentum transfer works exactly this way. The observable signatures are striking. Large-scale galaxy surveys have revealed what astronomers call the cosmic preferred axis. Galaxies across billions of light years show alignment patterns that shouldn't exist in a universe born from a perfectly symmetrical Big Bang. The James Webb Space Telescope's observations of distant galaxy rotations show this preferred direction extends to the very edge of our observable universe. This cosmic scale alignment matches precisely what you'd expect from a universe that inherited its parent black hole's angular momentum. But here's what makes this evidence so compelling. The standard Big Bang model predicts no such universal rotation. According to conventional cosmology, our universe should have emerged from an infinitely dense point with no preferred directions, perfectly isotropic and homogeneous. Any large-scale rotation should have been eliminated by cosmic inflation. Yet we see clear evidence of universal spin patterns that extend across the entire observable cosmos. The mathematics behind this spin inheritance are elegant. When you solve Einstein's field equations for the interior of a Kerr black hole, the resulting space-time geometry naturally produces an expanding universe with inherited angular momentum. The parent black hole's spin parameter directly determines how much rotation the child universe acquires. More remarkably, this rotation affects how galaxies form and align themselves over cosmic time. Think about what this means for galaxy formation. Instead of random orientations, galaxies should preferentially align with the cosmic spin axis inherited from the parent black hole. This creates observable patterns in how spiral galaxies orient their rotation planes and how galaxy clusters organize themselves across vast distances. Recent statistical analysis of galaxy orientations confirms exactly these patterns, something that's puzzled cosmologists for decades but makes perfect sense in a spinning universe model. Hey guys, just a moment before we continue. Don't forget to subscribe to our channel clicking on the notification bell and leave us a thumbs up so you don't miss out on our daily videos. The rotational energy inherited from the parent black hole also provides a natural explanation for dark energy, the mysterious force accelerating our universe's expansion. In a spinning universe, centrifugal effects create an outward pressure that mimics the effects we attribute to dark energy. This eliminates the need for exotic quantum fields or cosmological constants that have no known physical basis. Even our universe's apparent flatness becomes explicable through angular momentum inheritance. The spin from the parent black hole creates specific geometric conditions that naturally produce a flat universe, no fine-tuning required. This solves one of cosmology's biggest puzzles: why our universe has exactly the critical density needed to appear geometrically flat. The most exciting part? We're no longer limited to theoretical speculation about angular momentum in black hole universes. Right now, scientists are developing revolutionary experimental techniques to directly detect and measure the cosmic scale rotation that our universe inherited from its parent black hole. These aren't distant future possibilities. Some of these experiments are already underway in laboratories around the world. The breakthrough comes from understanding orbital angular momentum in ways we could never before. Traditional experiments could only measure linear momentum, how fast something moves in a straight line. But the 2025 quantum discoveries opened up entirely new methods for detecting orbital angular momentum, the twisting, spiraling motion that characterized rotating systems. Scientists have developed laser techniques that can create and measure twisted light beams, carrying orbital angular momentum, providing a direct window into rotational physics at quantum scales. Here's where it gets incredible. These same twisted light techniques are being scaled up to detect cosmic rotation signatures. Astronomers are now using specially designed telescopes that can measure the orbital angular momentum of light arriving from distant galaxies. Early results show systematic patterns in how the twisted light correlates with galaxy positions. Exactly what you'd predict if our universe inherited rotational structure from a parent black hole. But let's be honest about the limitations. These experiments are brand new, and many results haven't undergone rigorous peer review yet. The twisted neutron experiments are still in prototype phases, and the quantum simulators modeling black hole dynamics are pushing the absolute limits of current technology. Some critics argue that the angular momentum signatures we're detecting could have conventional explanations that don't require a parent black hole. The gravitational wave analysis is particularly challenging because the rotational echoes we're looking for are incredibly subtle, buried in noise that's orders of magnitude stronger than the signals themselves. Current detectors like LIGO are barely sensitive enough to hint at these patterns, let alone definitively confirm them. However, the scientific community's response has been electric. Major research institutions across the globe are racing to replicate and extend these findings. MIT's gravitational wave group is developing new analysis techniques specifically designed to isolate rotational signatures. The European Space Agency has fast-tracked additional funding for LISA's angular momentum detection capabilities. Even China's space program has announced plans for their own twisted light experiments aboard future space stations. What's generating the most buzz is how quickly other research groups are jumping on this bandwagon. Nature Physics is preparing a special issue on cosmic angular momentum for late 2025. Physical Review Letters has already accepted 3 follow-up papers expanding on the original quantum spin experiments. The prestigious Kavli Institute is organizing an international conference specifically focused on experimental tests of black hole cosmology. The quantum simulator experiments are attracting attention from unexpected quarters. Tech companies developing quantum computers realize that modeling black hole spin dynamics could advance their own technologies. This cross-pollination between cosmology and quantum computing is creating funding opportunities that didn't exist even 2 years ago. Perhaps most exciting is how the research is democratizing. Unlike previous cosmological breakthroughs that required billion-dollar space missions, many of these angular momentum experiments can be conducted in university laboratories. Graduate students at dozens of institutions are now building their own twisted light apparatus and quantum spin detectors. This grassroots explosion of research is accelerating discovery at an unprecedented pace. The timeline for definitive answers is remarkably compressed. Within 18 months, we should have enough experimental data to either strongly support or definitively rule out on the angular momentum inheritance model. LISA's launch in 2035 will provide the final word on gravitational wave echoes. But given how rapidly the field is moving, breakthrough discoveries could emerge much sooner. Thanks for joining me on this incredible journey through the cutting-edge science of cosmic rotation. If this blew your mind as much as it did mine, smash that like button and subscribe for more mind-bending discoveries from the frontier of physics. What other cosmic mysteries should we tackle next? Let me know in the comments below. And as always, stay insanely curious. If our universe really inherited its spin from a parent black hole, what do you think determines how fast that parent black hole was rotating? And could there be universes out there spinning much faster or slower than ours? Let me know what you think in the comments below, and then you should check out our videos on the end screens.